Section 6.1, areas between curves. Section 6.1, areas between curves. In Chapter 5, we started by finding the area under a curve y equal f of x over a certain interval ab, where the function was positive. You might remember that we had a very simple graph to start with. We just had some basic function. There's our a and b, and it was above the x-axis. In reality, that whole time, we actually found the area between the function y equal f of x and the line y equals 0, which is really just the horizontal axis. So now we are scaling that up. The next logical step is to find the area between two curves, y equal f of x and y equal g of x. As a simple picture, just imagine both of those curves are above the x-axis, and you have AB, and you just want to find the area between them. If you think about just the picture that I've drawn here, you can imagine that, well, if you know the area below f of x, and you also know the area below g of x, how would you find what's between them? You would just use subtraction. That's it. So in terms of the infinite limit of a Riemann sum, we would have capital A for this area is equal to the limit as n approaches infinity of the sum from I equal 1 to n of the difference of these function values, f of x sub I star minus g of x sub I star. That difference gives you all of the heights, and then delta x is still our width. And then we would have an infinite number of rectangles at this point that we would then add up. We can then define that in terms of the definite integral, and we get this definition. The area, capital A, if we want to call it, of the region bounded by the curves y equal f of x, y equal g of x, and the lines x equal a and x equal b, those are those vertical lines that are implied, where f and g are continuous and f of x is greater than or equal to g of x for all x in the interval ab is, and we have our integral from a to b of the difference f of x minus g of x, that's our integrand, and then dx saying that we are integrating with respect to x. So this is it. This is the only concept for this section. Now we're just going to look at some examples. So first, find the area of the region bounded above by the function y equal e to the x, bounded below by the function y equal x, and bounded on the sides by x equals 0 and x equal 1. A big suggestion for, in fact, the majority of this whole chapter, chapter 6, draw a sketch. Have some sort of idea of what these functions look like. So y equal e to the x, some things that we know about it. It goes through the y-axis at 1 because e to the 0 is 1. And then it's exponential, so it curves up like this. So there we go. From x equals 0 to x equal 1, we could have a little bit of an idea as to what that looks like. If we say this is 1 and that is 1, there's our exponential function. And then the other graph, y equal x, that's just a line with y-intercept 0 and slope 1. So we could say this is 1, 1 here. There's our line from x equals 0 to x equal 1. So we've got y equal x, we've got y equal e to the x, and you can think, well, they don't intersect in that interval because they have different y-intercepts, and also e to the 1 is greater than just the x value of 1. So our area is really just that little bit. So you can see that e to the x is above y equal x in that whole interval. So e to the x is greater than x for all values of x between 0 and 1, which means by our definition, this area that we are looking for will just be the integral from 0 to 1 of the top function, e to the x, minus the bottom function, which is just x, and then we are integrating with respect to x. You'll probably start to notice that I'm dropping the parentheses that you may see in these definitions and also what you might have seen in chapter 5. The reason being is there really is no other way to interpret this. You don't need parentheses there. We have to understand that the integrand is everything that is between the integration symbol and the dx, the differential. So then just using antiderivatives, the antiderivative of e to the x is just e to the x. The antiderivative of x is x squared divided by 2. We don't have a constant of integration because we have limits. And so I need to plug in 1 first to both of those functions and then 0. So I get e to the 1 minus 1/2 minus e to the 0, which is 1, and then minus 0. And so then I end up with e to the 1, or just e, minus 1/2, and plus 1. So we can say e plus 1/2. Here's another example that I've taken from the homework. Capital R is the region bounded by the functions f of x equal 3 over x and g of x equal to negative x over 3 plus 10 over 3. Find the exact area of R. So note, if you aren't told which function is above the other, or, as we also have in this example, what the limits of integration are, you need to find all of that out first. So we do need to do some sort of sketch and some algebra work to have some things to even start the integration process. So let's start with graphing. And let's see. F of x equal 3 over x. That has a vertical asymptote at x equals 0. It's going to be a hyperbola shape. We can plug in a couple of numbers to help us out with this. Like how about 1 and 3? When x is equal to 1, f of x is equal to 3 divided by 1, which is 3. So I can draw a little dot at 1, 3 for f of x. Also, when x is equal to 3, f of x is equal to 1. And so you would have a hyperbola shape like this. And then also let's look at some negative values. When x is equal to negative 1, you would get negative 3 for f of x. And when x is equal to negative 3, you would get negative 1. So this is definitely something that you want to be able to do. Notice I'm purposely not using a program like Desmos to do this. I'm demonstrating this in front of you to show you that, first of all, you can do this, and second of all, you need to do this. This is something that you should be able to do on your own just to have an understanding of how these functions work. There is also a horizontal asymptote. Think as x gets larger in a positive or negative direction, you essentially have 3 over infinity, which is 0. So we have this to start with for f of x. Now let's see if we can draw g of x. G of x is just a line. It has a y-intercept of 10 over 3, which is really just 3 1/3. And then the slope is negative 1 over 3. So let's stick with red for that one. So y-intercept is 3 1/3, which we could say is there. And then I have to go down 1 unit and then to the right 3 units. So if I go down 1 and then to the right, that gives me this point. Okay, and then it would keep going to the right. And then I would also have this line extending to the left like that. So here's something that we can notice. the red line and the blue curve, they intersect. It looks like maybe we could assume that the intersection is 1, 3, but we're actually going to find out if that's true by doing some algebra work. And then if we also remember that this blue curve actually keeps continuing, they're probably going to intersect again. So we're going to need to figure that out. They did also say that we want the area bounded by the functions. So the only way to interpret that is there is a finite beginning and ending to this. If you think about anything else that's happening in this graph, like what about between there? You don't have anything that's actually bounded. That's continuing infinitely. You already know the answer for how much area that is. It's infinite. So we really are just looking at the picture that we have in front of us. So we need to figure out, now that we've seen this, we need to figure out where they intersect. Once we've done that, that's going to help us with our limits of integration. And then by my picture, now I can see that g of x is actually greater than f of x in this particular interval. So we need to find the limits of integration. And sometimes you're going to have to find those limits by setting the functions equal to each other. Other times you can see that from the graph. Like we may be able to find out that 1, 3 is a point of intersection, but we definitely don't know what the one on the right is. So that means I have f of x, which is 3 over x, equal to g of x, which is negative x over 3, and then plus 10 over 3. So an easy way that you can try to get started with this is multiply both sides by the least common denominator. In this case, that would be 3 times x. So I'm going to multiply everything by 3x. So 3 over x, when multiplied by 3x, would just leave you with 9. Negative x over 3, when multiplied by 3x, would give you negative x squared. And then 10 over 3, when multiplied by 3x, would leave you with 10x. So all I did was just distribute to each of those terms. So now you can see that this is a quadratic equation. The only way that you can solve a quadratic equation is getting everything on one side, 0 on the other, and either using factoring or the quadratic equation. So if I get everything on one side, x squared minus 10x plus 9 equals 0. I can factor this, x minus 1, x minus 9. Negative 1 times negative 9 is positive 9. Negative 1 plus negative 9 is negative 10. And you can see we definitely do get x minus 1 equals 0, which means x is equal to 1. So exactly what we suspected. And then we now also find the other one, x equal to 9. And this gives us our limits of integration. All we need is just what are those x values? So 1 and 9 become our limits. So now we can use all of this to find our area. They called that area or region R. It's the integral from 1 to 9. We need to now remember that g of x, the line, is above f of x. So the first function in our subtraction has to be negative x over 3 plus 10 over 3. And then I have to subtract my second fraction. So I have to subtract 3 over x. And then dx. So now, integrating using antiderivatives, negative x over 3, remember that's negative 1/3 times x. So then I would raise x's power from 1 to 2, and then divide by 2. This is going to leave me with negative x squared over 6. And then plus 10 over 3. The antiderivative of that is 10 over 3 times x. And then minus 3 over x, the antiderivative of that, the minus 3 is a constant, And now I need the antiderivative of 1 over x, which is the natural log of x. And then I have to plug in my limits of integration. So then I have negative 9 squared over 6, so negative 81 over 6, plus 10 thirds times 9, which will be 10 times 3 or 30, minus 3 times the natural log of 9, and then minus, now plugging in 1, I get negative 1/6, plus 10 thirds, and then minus 3 times the natural log of 1, but the natural log of 1 is 0. And so now I can just simplify what I have. Something to keep in mind with this, from the homework, they are asking for an exact value, which means if I've got some fractions, I should try to just write something using fraction notation and also keep that natural log of 9 as it is. Don't get a decimal for that. So let's see if I can just clean this up a little bit. I'm going to be taking negative 81 over 6 and adding 1 over 6. That leaves me negative 80 over 6. So I should write that. And then I have plus 30, but then I'll have to subtract 10 over 3 from that. So that's subtracting 3 1/3. That leaves me with 26 2/3. And then I have my minus 3 natural log of 9. And it's at this point we probably want to get a common denominator for those first two terms. So I could divide 80 by 2, which is 40, and 6 by 2, which is 3. And then 26 2/3 is the same thing as 26 times 3, which is 78, plus 2, which is 80 over 3. And so when I add negative 40 over 3 plus 80 over 3, that leaves me 40 over 3. So I can say that my final answer is 40 over 3 minus 3 natural log of 9. So in general, it is a good idea to graph the functions before jumping into integration. You need to figure out which curve is above the other and also find out if in a certain interval the functions switch, meaning if you had f of x over g of x, maybe after a certain point they switch and g of x is above f of x. If you end up with something like that, you can call them complex regions because there's more than one region in the total area. Split up the integration and add the individual areas. We're going to see that in the following example, which comes from the homework section called Areas of Compound Regions. There's a couple of different homework sections on just this one topic. So this example says, find the area of the region that is bounded by the line f of x equal negative x minus 1 and the curve g of x equal to 1 minus x squared over the interval negative 2 to 0. So again, I'm going to start this by sketching a graph. I have f of x is negative x minus 1, so its y-intercept is negative 1, and the slope is negative 1, which means it will go down 1 and then over 1 to the right. So I'll start with the y-intercept at negative 1. The next point would be at 1 comma negative 2, and then I would just have a line connecting those two. So there's f of x. And then for g of x, it's a parabola that is opening down. And you could just plug in a couple of numbers to get an idea of what this looks like. So let's see. If I plug in 0 for x, I get 1 minus 0, which means that I do have a y-intercept at 0, comma 1. If I plug in 1 for x, then I would get 1 minus 1 for g of x. I would get the same thing if I plugged in negative 1. And then if I just go out a little bit more, if I plug in 2 into g of x, I would get 1 minus 4, which is negative 3. So a point down here. And then if I plug in negative 2, then I would also get negative 3. So there's my graph of g of x. And the region that we're focused on is in between 2 and 0, negative 2 and 0. So let's actually visualize that with maybe some dashed vertical lines, or if you want, you could use some solid vertical lines. So we're really only focusing on this part of the graph between negative 2 and 0. So I just want to know, what is this area? Everything else that was part of the graph was just there as a guide. This is really the most important part. So what you can see, and obviously color coding here helps as well, f of x is above g of x between negative 2 and negative 1, but then they switch. G of x is above f of x between negative 1 and 0. You could also check that those intersections are correct, really just the one that we need. So if we set our functions equal to each other, negative x minus 1 for f of x equal to 1 minus x squared for g of x, then getting everything on one side, I'd have x squared minus x and then minus 2 equal to 0. And this ends up with x minus 2 times x plus 1 equals 0. So x equal negative 1 is an intersection, and so is x equal 2. So they definitely intersect at negative 1. And then we can say f of x is greater than g of x for x between negative 2 and negative 1, but then they switch. G of x is greater than f of x for x between negative 1 and 0. So what does this mean for our area? All I'm going to do is just split up my integration. I'm going to have an area for one region, we can call this R1, and an area for the other region, R2, and then I'm just going to add them up. So the total area is equal to the area in region 1 plus the area in region 2. And the way that I would find the area for region 1, the limits of integration would be from negative 2 to negative 1. And then since f of x is greater than g of x, that would be f of x first, negative x minus 1, minus g of x. And I recommend using some parentheses here, mainly because with g of x, you're about to have a 1 minus x squared. And you want to make sure that you remember that the 1 changes sign to a negative 1, and the negative x squared changes sign to a positive x squared. So that's f of x minus g of x. But then the other integral for region 2, the limits would be from negative 1 to 0, and then you would have the function switched. So you'd have 1 minus x squared first, and then minus negative x minus 1, and then dx again. So I'm going to simplify my integrands, and then we can use antiderivatives and then evaluate. And you can't assume that the antiderivatives are going to be the same, mainly because when you subtract, things change when the order of subtraction changes. So simplifying the integrand in the first integral for region 1, I have from negative 2 to negative 1, and then I have negative x minus 1 plus another negative 1, but then plus x squared. So this leaves me with x squared minus x minus 2 dx. And then the other integral from negative 1 to 0, I would have negative x squared plus x and then plus 2. You can see that the integrands are actually opposite signs. So then, just doing some antiderivative work and evaluating, we can get a final answer. I'm going to add a page here because I'll probably need a little bit more room. So antiderivative of x squared is x cubed over 3. Antiderivative of x is x squared over 2. Antiderivative of 2 is 2x. So I'm going to have x cubed over 3 minus x squared over 2 minus 2x evaluated at -1 first and then -2. That gives me the area of the first region. And then for the second region, I have negative x cubed over 3 plus x squared over 2 plus 2x. And that will be evaluated at -1 first. And then, I switched that up. 0 first and -1 second. So plugging in -1 first to my first antiderivative, I get -1 cubed is -1, so -1 third, minus -1 squared is still +1, so I'd have -1 half, and then plus 2. Plugging in -2, I get -8 thirds, and then minus 4 over 2, or 2, and then plus 4. And then I have from the second region, I have to plug in 0 first. That's just going to be 0 plus 0 plus 0. And then plugging in -1, I would get a +1 third plus a half, but then -2. So then -1 third minus a half is -5 over 6 plus 2. And then I would have, after subtracting these, I'll have plus 8 thirds. And then a 2 minus a 4, that's a -2. So I can already see that I'm going to get some things further canceling out. And then the zeros, and then I have minus what was left. And that's going to turn into a -1 third, a -1 half, and a +2. So then I have -1 third, -1 half, and then +2. So I've got -5/6, and then I've got minus another 5/6 there. That leaves me with -10 over 6 plus 8 thirds, and then +2. -10 over 6 is the same thing as -5 over 3. Adding that to 8 over 3, that's just 3 thirds or 1 plus 2, and that's 3. So the total area between those two curves is 3. Something of a comment about our result, you might notice that we got a positive answer for our area. But if you look at this picture, it certainly looks like there's more area below the x-axis. So you might be thinking, shouldn't this be a negative area at the end? What you want to think is, in this process of subtracting, when we have f of x above g of x, you're really finding the area that's between f of x and the x-axis. And then you are subtracting the area that is between g of x and the x-axis. You're taking a positive answer and subtracting a negative answer. When you do that, subtracting a negative, it just turns into addition. So you truly are just finding the positive distance of area between these two functions, in essence. So keep that in mind when you're getting your answers. It's a good way to maybe check that what you're doing is correct, and also just have an intuitive sense about the positive and negative nature of these areas anyway that we saw back in Chapter 5. So now, as we are finishing Calculus 1, we are going to start to see that the ideas we've learned can be expanded to much broader terms. For example, we've usually had y as the dependent variable that depends on x, which we've called the independent variable. But that was just a choice in notation that came from naming the horizontal axis x and the vertical axis y. This is also just a choice for how we observe things. However, if we rotate images 90 degrees, then we can change our perspective and therefore change the names for independent and dependent variables. So for example, if we took the graph for y equal x squared, a parabola that opens up, that would be this graph here on the left. If we took that and rotated it 90 degrees clockwise, we would get a parabola that opens to the right. This is the picture that's on the right-hand side. If we don't switch the labels for the horizontal and vertical axis, meaning if we keep horizontal as x and vertical as y, then the new graph has an equation that is x equal y squared. You might have learned this in algebra when you talked about parabolas or circles and hyperbolas and ellipses, that you can have them orientated in any way. We might say that the graph on the right is not a function because we would say, well, it doesn't pass the vertical line test. But we actually have to be careful at this point. What we really mean by saying that is not a function is it is not a function of x, but the graph that is on the right actually is a function of y. So this graph on the right is x as a function of y. What we've done is switch the role of who is the independent and who is the dependent variable by doing this. And this is actually important because while we could find areas related to the first graph, why shouldn't we be able to find areas related to the second graph? Things shouldn't have to change just because we've flipped a little bit of the ideas of what these pictures look like. In fact, you should think that that seems obvious because if you wanted to find the area related to the function that's on the right, you could just rotate your page 90 degrees and then you could just go back to what we've been doing before. But we don't want to do that. The way that we could find areas related to the image on the right is if we integrate with respect to y. And this becomes the main idea, is we don't need to worry about y as a function of x. We can just start doing integration relative to whatever our independent variable is. So let's see that in a very specific example. Find the area enclosed by the line y equal x minus 1 and the parabola y squared equal 2x plus 6. Hint, since the parabola that was stated has y squared, we should make both of these graphs x as a function of y, meaning get x by itself in both equations. So y equal x minus 1, that's the same thing as saying y plus 1 is equal to x, or we could say x is equal to some function of y, which is y plus 1. Then we could also say for the other equation, y squared equal 2x plus 6. I could subtract the 6, so y squared minus 6 equal 2x. And then I could divide by 2. I would get 1/2 y squared minus 3 equals x. So I could say that in this case, x is equal to, let's say, g of y, which is 1/2 y squared minus 3. So we really just have two functions of y. And I'm intentionally using f and g to relate this to what we saw at the beginning of this lesson. So now I want to find the area enclosed by those curves. So just thinking of what we did before, we should draw a graph. And then we should also try to see where these curves intersect. And then we can figure out our limits of integration and which function has to be quote unquote above the other function. So to help us with our graph, I'm actually going to find the intersection points first, since we know how to do that. Let's just see if they intersect. This means we would set y plus 1, the first equation, equal to 1/2 y squared minus 3. So then I should get everything on one side. So 0 is equal to 1/2 y squared minus y minus 4. I can multiply everything by 2. And I get 0 equals y squared minus 2y minus 8. And then I can factor y minus 4, y plus 2. And then I can see that y minus 4 is equal to 0 and y plus 2 is equal to 0, which means that y is equal to 4 and y is equal to negative 2. That's where these two graphs would intersect. So then I'm going to do some graphing. I'm going to have a line, and I'm going to have a parabola, and this parabola is similar to the one that I had before. It will open to the right. The way that you know it opens to the right is because the y is squared and it has a positive leading coefficient. So I'm going to have a line, a parabola that opens to the right, and they have to intersect at y equal 4 and y equal 2. Oh, sorry, y equal negative 2. 2, 3, 4. There's y equal 4. Y equal negative 2. Let's start with the line. So I'm going to start with, let's say, when y is equal to 0. When y is equal to 0, then x will be equal to 1 for the line, which means I would have a point here. And then if I want to plug in another number, how about if I plug in y equal to 1? When y is equal to 1, then I would get x is equal to 1 plus 1, or 2. So then I get another point here. So that becomes the 2 points that I need to make my line. And I'll continue them out enough so I'll also be able to see the intersection points. So that's x equal y plus 1. Then for my parabola, we can use similar numbers. How about when y is 0 for the parabola x equal 1/2 y squared minus 3? When y is equal to 0, then I get x is equal to 0 minus 3, or negative 3. So I get a point on the negative x-axis at negative 3 comma 0. And I could do a couple more points here, but we already sort of know that these things are going to intersect at some point. So how about just 2 more points, and then we'll have enough as a guide. So let's say when y is equal to 1. Then I would get 1/2 minus 3. Maybe that subtraction's a bit too complicated, so if I use y equal 2, that gives me a little bit of an easier number to use. So when y is equal to 2, then x is equal to 1/2 times 4, which is 2, minus 3. So I get negative 1. So at y equal 2, I get x equal negative 1 as a point, which means I actually get the same thing for negative 2. So then I can just draw a parabola shape, and then keeping in mind that these things have to intersect at 4, meaning y equal to 4, like that. So the area that I'm looking for is here. Okay, so here's what we can keep in mind. I could find the x values of those intersection points and then figure out a way to integrate with respect to x. The problem about doing that is you would be trying to figure out one function minus another function that acts vertically. And you can see that that would be tough on this lower part, or I should say left-hand part of the parabola, because you'd have to have a parabola minus itself, which means now you need to split that parabola up into 2 functions of x. So the reason why integrating with respect to y is more preferable in this case is it reduces the amount of work. And while you're looking at this picture, I want you to do something that I've actually been doing this whole time that I've been graphing this. Every time that I needed to graph something, I've been turning my tablet so I could do graphing a little bit the way that I'm used to. If you are looking at this screen on your computer, you can rotate your head 90 degrees to the right, and you can see that the blue line is above the green parabola. And you want to keep that in mind because that's the way that we've been thinking of areas, is one function above another. So we can't really use words like above or below here, mainly because we need to think horizontally. So we can say things like right and left. And this is all going back to the ideas of one function being greater than another function. So here we can see that f of y, which is equal to the line y plus 1, that is to the right of g of y, which we said was the parabola 1/2 y squared minus 3. In the interval where y is between -2 and 4. So what this means is f of y is greater than g of y. And they are equal at their intersection points. So we have this idea throughout that whole interval. So I don't have two complex regions that we had in the last example. I do just have one. And now my integration becomes the lower limit, -2, to the upper limit, 4. The greater function, f of y, which is y plus 1, minus the lower function, which is 1/2 y squared minus 3. And then I have to integrate with respect to, you only have one choice here, y. Your functions are defined in terms of y. So you are integrating with respect to y. So then this all works out exactly as we've done before, it's just we have a different variable. So I'm going to simplify my integrand. I would have y1, and then that's going to be minus a -3, so I'd have a 4 as my constant. And then this will be a minus 1/2 y squared dy. It doesn't matter the order in which you write these now because you're going to turn all of this into a number. So I'll just do my antiderivatives with respect to y. So the term y is y to the first. I would just increase the power by 1 and then divide by the new power. And then the constant 4 wouldn't become 4x, it becomes 4y, because again, y is your independent variable here. And then minus 1/2 y squared, the antiderivative will be minus 1/6 y to the third. And then I need to plug in 4 first and then -2 second. So I get 4 squared over 2, which is 16 divided by 2, or 8, plus 4 times 4, which is 16, minus 4 cubed, which is 64 over 6, and then minus, now -2 squared is 4, divided by 2 is 2, plus 4 times -2, so minus 8, and then minus 1/6 times -2 cubed, that's -1/6 times -8, which would be positive 8 over 6. So then just simplifying all that's left, 8 plus 16 is 24, minus 2 is 22, plus 8 is 30. Negative 64 over 6 minus 8 over 6 is negative 72 over 6, which is 12. So this is 30 minus 12, which is 18. If you want to do something to see if this is correct, you could do this whole problem by just looking at the area between y equal x plus 1 and y equal 1/2 x squared minus 3. So you could do that on your own compared to area between y equal x plus 1 and y equal 1/2 x squared minus 3. All I did was just switch the variables from the functions that we had. And you can orientate this in a vertical fashion, and you can see that you get the exact same answer of 18 at the end.